Okay, so this is section 1.6 out of Griffith's quantum mechanics, and it talks about the uncertainty principle, which is a pretty interesting section. It definitely confuses a lot of people, and I think it sounds crazier at first, but the more you think about it, the more it kind of starts to make sense. And I think Griffith does a pretty good job illustrating that with 1.8 and 1.9. And it kind of gets into the main theme that I think people have problems with, which is a lot of people like to kind of hold on to this particle nature of reality. But when you start thinking of things in terms of waves, some of the things in quantum mechanics that seems anti-intuitive kind of starts to make more sense. So if we think of it like a classical wave, in 1.8 we have a guy that's shaking this rope up and down and kind of creating this standing wave, if you will. And if you asked, like, what is the position of the wave, that question doesn't make a lot of sense because the wave is kind of everywhere. It's not localized to one particular spot, or at least in a region. It's really spread out from about 10 feet to 50 feet or so. So that's not a question that makes a whole lot of sense. But if you ask what is the wavelength of this wave, well, that's a lot easier to do because this is a repeating pattern. You can find where it repeats, and you can determine the wavelength. So that's not a huge deal. But in figure 1.9, it's a little bit different. Here, it's a pulse wave. So the little stick figure guy gives the rope a quick jolt up and down, and then it sends this pulse wave down the rope to the other side. And in this case, the wave is a little bit more localized. So if you said the wave is at about 25 feet, okay, we kind of get what you're saying. But if you asked what the wavelength was, well, this isn't a repeating function. So what does that even mean? Like, it's not a periodic function. So this is basically demonstrating the uncertainty principle in classical waves. Because even in classical waves with ropes or water, sound waves, you actually have an uncertainty principle. So from that, it's not a huge stretch to think of an uncertainty principle for quantum mechanics. And with quantum mechanics, we often relate some of our quantities, such as wavelength and momentum, by the de Broglie formula. There's a lot of debate on how you actually say this guy's name, but regardless, you know who I'm talking about. So h over lambda, or if you want to do it in terms of the reduced Planck constant, P is equal to 2 by h bar over lambda. Okay. So if we want to define our uncertainty, sigma x, sigma p is greater than or equal to h bar over 2. And these sigmas are exactly what we talked about in the probability section of this playlist. So if you go back to where we talked about the probability, we talked a little bit about the standard deviation. And I think I mentioned that's something to keep in the back of your mind. And, well, here it is. Okay, so that is our uncertainty principle. And it's a little hand-wavy right now, but the first section of this textbook is just kind of familiarizing you with the concepts. And then in the later chapters, we're going to hit the math a little bit harder than we are currently, but we'll have a more rigorous and justified account for all of this. Okay? So that's essentially what we're getting. Hopefully that all makes sense, and the next video should be a good practice problem. Looks like problem 1.9 if you want to try it out first. If you enjoy this type of video and you're enjoying this quantum mechanics series, Please like the video and subscribe, and I'll continue to post more.